So here we're given the Haber process and the Ostwald process. In the Haber process, hydrogen gas is obtained from the chloralkali process. It doesn't really matter how you got the hydrogen gas, but there they're telling you. And we'll learn about the chloralkali process later on in the year when we do electrochemistry. It's reacted with nitrogen gas to produce some ammonia. The ammonia gas is produced in this process is the starting material for the Ostwald process. So we use this ammonia to start over there. For the preparation of nitric acid is the end product. It's a three-step process, so the Ostwald process. The steps involved in the reactions are given over there. They tell us some conditions about the reactions. What type of a reaction, endo or exothermic, is the forward reaction of each of the steps where delta H is given. So delta H here, 0 is biggest, so this is an exothermic because it's negative. Here again we've got an exothermic reaction. And here again we have got an exothermic reaction because in every case delta H is a negative number. When considering the effect of each of the following changes, answer only increase, decrease, or no effect. What effect does the use of an ion catalyst have on the yield of ammonia? Now a catalyst will make the reaction go faster, but it does not change the yield at all. It will just create the same equilibrium more quickly. So what is the effect? It's no effect at all. What effect does increasing the temperature have on the yield of nitrogen monoxide in the first step of the Ostwald process? So now what we're trying to do is we're taking a look. If I increase the temperature on this reaction, will I get more or less product is really the question. So if I increase the temperature, remember an increase in temperature always favors endo. We've just said that this reaction is an exothermic reaction. Sorry, that's endo. So therefore it favors the reverse, which means what's going to happen to my yield of NO? That is going to decrease. What effect does increasing the pressure have on the solubility of NO2 in the last step of the Ostwald process? So I'm over here, I'm putting NO2 into water, and now I'm going to increase the pressure. Pressure, we're going to take a look at gas moles. So I have got 3 gas moles on the left and I have got 1 gas mole on the right. Increasing pressure will always favor the least gas moles, so it is going to increase the forward reaction, which is the dissolving of NO2 into water. So it is going to increase the solubility. What effect does reducing the volume of the vessel have on the rate of oxidation of ammonia in the Ostwald process? So ammonia is oxidized in this first step over here, and now we're going to reduce the volume. What does reduce volume really mean? It means increase the pressure. And so now again we're going to take a look at gas moles. On the left hand side I have got 9 gas moles. On the right hand side I have got 10 gas moles, which means that if I increase the pressure by reducing the volume, I will favor the reverse reaction. So what does it have on the oxidation? Oxidation is the adding of the oxygen. So what effect does it have on the forward reaction? It actually decreases the forward reaction of that particular reaction. So that is going to be decrease. Now we have a graph showing the distribution of molecular energies at constant temperature. Now this is the Maxwell-Boltzmann distribution, and you will remember that normally on a Maxwell-Boltzmann distribution they're going to have the activation energy over there, let us say, at a point. And these are all the particles that are able to react at a certain temperature. So Maxwell-Boltzmann distributions are always at a certain temperature, and that is the number of molecules that have a certain amount of energy. They now add a platinum catalyst to the first step of this process. Copy the graph into your answer book and use it to explain how the catalyst increases the rate of the reaction. All that a catalyst does is it reduces the activation energy. So with the catalyst, I'm going to have a lower activation energy, and therefore more particles will have enough energy in order to be able to react, and therefore the reaction will go faster. How will the mass of the catalyst change during the course of reaction? It will not. It will remain constant. Here we have a reaction. Again, it is the Haber process, and they tell us quite a lot about it. In the Haber process, we've got 8 moles of nitrogen, 11 moles of hydrogen are introduced into a certain container of 10 decimeters cubed at a certain temperature. The container is sealed immediately after the gases are added. The graph represents the change in the number of moles of gas in the reaction vessel over 35 minutes. Use the figures from the graph to determine the equilibrium constants of hydrogen, nitrogen, and ammonia at 8 minutes. So we're going to go over here, and we're going to take the number of moles, and it's going to be 8 of hydrogen, and it is going to be 7 moles of nitrogen, and it's going to be 2 moles of ammonia. Give one advantage of performing the process at high temperature: it will increase rate, so it will go faster. So we're going to increase the rate. What change was made to the equilibrium mixture at the time of 10 minutes? So at 10 minutes something happened. The only thing that's distinctly different is this huge jump in hydrogen. So obviously some hydrogen was added to the container. Also, I can see that after that I got less hydrogen and less nitrogen and more ammonia. In other words, I favored the forward reaction, which makes sense if I put some more hydrogen into that reaction. Explain why the number of moles of various gases changed as they did after the change at 10 minutes. So, firstly, we added reactant, therefore forward favored. Therefore, H2 and N2 decreased, and NH3 increased. At a time of 20 minutes, a further change was made to the equilibrium mixture, which brought about a permanent change in the equilibrium constant Kc. Explain what that change must have been. Well, firstly, if we're changing Kc, it must be a change in temperature. What happened at 20 minutes is that we got less of the reactant and more of the product. So in other words, we must have favored the forward reaction. So forward was favored. This reaction from the previous page we happen to know is an exothermic reaction, which means that we must have decreased the temperature. They would need to give you whether it was an exo or endothermic reaction if it hadn't been on the previous page. What would have happened to the equilibrium constant? It would have, Kc would have increased. Why? Because we have got more product and less reactant. The reaction of methane with steam produces hydrogen gas. The equation is given. Initially, we put 1 mole of methane and 2 moles of steam in a certain container. The mixture contains something. Calculate the equilibrium constant. So I'm going to do a Rice table. I'm just going to do it underneath over here. My ratio is 1:2:1:4. My initial is I started off with 1 mole of methane and 2 moles of steam. They are put into a 5 decimeter, so it's already been converted into decimeters cubed. So I've already got a 5 decimeter cube container. Equilibrium is established, and the mixture contains 0.3 moles of carbon dioxide. I need to link the consumed of the reactants with the equilibrium of the products, and I go 1:4 as 0.3 is to 1,2. 1:2, 1:1 as that's to 0.6, and 0,3. So that's where the ratio is in that little sausage over there. And now I do a subtraction. 1 minus 0,3 is 0,7. 2 minus 0,6 is 2,4. I didn't start with any of that or consume any of that. And now to get the concentration, I am going to work out each of these by dividing by 5. Once I have all those concentrations, I can now say Kc is equal to concentration of products, CO2, it's a gas, H2 is a gas, I need to raise it to the power of 4, over CH4 and H2O squared, and that is equal to 0,06, 0,25 to the power of 4, 0,14, 0,48, and square that. So once I calculate that out, I get 0,073. Decide what can be deduced from this. The reverse reaction is favored because that's a small value. So reverse reaction is favored. Consider the following equilibrium reaction. Got all of that information given over there. And they want you to calculate Kc once again. So let's see how we can place that information. We have been given 9 moles of nitrogen, 15 moles of hydrogen, nothing of ammonia. The ratio is 1:3:2. It's all in a 500 centimeters, so it's 0,5, 0,5, 0,5 decimeter cube container. The temperature is now raised to 405, resulting in 8 moles of ammonia being present at equilibrium. So at the end I've got 8 moles of ammonia, and they want Kc, so I'm going to link the consumed of the reactants and the equilibrium of the products. 2:3:1 is as 8:12:4. 9 minus 4 is 5, 15 minus 12 is 3, and then we have to divide it by 0,5, so it's 10, 6, and 16. Kc is equal to concentration of products raised to the power of the coefficient divided by the concentration of the reactants raised to the power of their coefficient, and we substitute in those values and you get 16 squared divided by 10 times 6 squared, and we get, sorry, that was 6 cubed, and it's 0,12. And again, that gives me a small value for Kc.